All right, welcome to chemistry and welcome to chapter 1 of this course. We're going to be looking in this chapter at basically just an introductory to what is chemistry and talking about the fact that chemistry is a physical science. We'll be talking about matter and physical objects, basically non-living things. And we're going to be looking at the change that occurs in those non-living objects. So obviously the title of this first chapter is Matter and Change, and chemistry is all about matter and the changes and the reactions that occur in that matter. Okay, so we're going to dive in here. I'm going to walk you through this, what is called an interactive reader, highlight some things for you. You can follow along with me with your own if you've printed it out or if you have it on your computer, and we'll answer some questions as we go, and then you can use this as a study tool. Okay? All right, you can see here in each of the three sections what we're going to talk about. Talking about chemistry being a physical science, we're going to be talking about matter and its properties, and then we're going to be focusing on basically the elements that we get to discover, we get to use, we get to manipulate, we get to turn into technology that is both beneficial and useful for us. Okay? All right. At the beginning of each chapter, the interactive reader, there are always going to be some previous concept questions, and these are going to just test your ability to think about maybe something you've learned in the past or something maybe some common knowledge that you might be aware of. It's just an opportunity for you to think and warm up your thinking a little bit about chemistry and what we've been talking about, because it's often going to tie into what we are going to talk about in the new chapter. Okay, we're in chapter 1, but still these are some basic concepts, and you're going to want to address these questions here before moving on. So you can pause the video at this time and just answer those questions to the best of your ability. This one is just asking, what is science? So just use your knowledge that you have right now, your existing understanding of what science is and what scientists do. Okay? And then here we're just using your ability to compare and contrast. That's all. Just look at a metal spoon, a plastic spoon, name some of the properties that they have, maybe that are in common or that are different. Because we're going to be looking at properties. We're going to be looking at the chemical properties and the physical properties of different objects and the chemicals that make them up. Okay? Alright, you've done the review questions, and let's dive into section 1 here of this chapter, talking about chemistry as a physical science. What we mean by that simply is that a physical science is going to be looking at objects and matter, materials, basically focusing on non-living objects. Biology, obviously you would focus on living organisms, but here in chemistry and physics and other physical sciences, you're going to be looking at predominantly non-living. Obviously there's lots of chemistry in living organisms, but we're going to be focusing on the non-living matter that makes up this world. Okay? So here's one way to define chemistry, and it is the study of the structure and properties of matter. Matter just being the stuff, the chemicals, the materials that make up this world. Okay? And we're also going to be focusing on the processes that matter undergoes. That could be as a result of a chemical change or a physical change or some type of reaction. And we're definitely going to be focusing on the energy that accompanies those changes and those processes. So a lot of chemistry is focusing on energy. Energy gained, energy lost. Why do we have compounds in this world? It's all dealing with energy. Okay? Throughout the interactive reader, there are going to be some different questions. Here's one that's called a reading check. And so it says, write 2 questions that a chemist would try to answer about a material called chemical X. And you can look back up here. They give you lots of possible questions and ideas. And so you're going to pause the video right now if you want and answer that, or you can answer it later, and then I'll see that response that you filled in when you submit this. Okay? We're going to be talking about chemicals. Obviously, chemistry is the study of chemicals and any substance with a definite composition. We'll talk about that definite composition later on as we actually do some calculations with that. Okay, you're going to see some patterns as a result of that definite composition. Okay, for example, sucrose or common sugar, it is a compound that has a definite composition, a definite ratio of certain elements in it. Okay? Throughout the interactive reader, you're going to see these main keys, these main key points here that are kind of highlighted for you. So don't miss those and pay attention to those. Chemistry, as we often do in science, we like to break things down, we like to divide things, we like to categorize things. So chemistry is divided into several different branches of chemistry, meaning several different fields of chemistry. Somebody might focus on organic chemistry, which is basically looking at material that is made up of carbon. All right? We might say living organisms. Inorganic chemistry, anything that is non-organic, so that doesn't have carbon-based materials in it. And the physical chemistry would be just looking at matter in general, like what we're going to be focusing on. Analytical chemistry is the identification of materials, so maybe using some data and some information to then identify what is in a particular material. Biochemistry is the overlapping of biology and chemistry. As I mentioned already, there's a lot of chemistry that happens in our bodies and in all living organisms. And then theoretical chemistry is how can chemistry be used for us to make new materials that are going to be useful, advancing technology, etc. So how are properties going to be developed into making new materials? That's happening all the time. Okay, those guys, those theoretical chemists, are kind of on the cutting edge of the knowledge of chemistry. Okay, the information that's in chemistry. All right, so again, you just need to be familiar with these sort of branches of chemistry. Be aware that there are what they've designed here is 6 different branches of chemistry. Okay. In chemistry, as in any science, there's going to be research involved here, and the goal of research is just to expand our knowledge about that particular field. Okay? In chemistry, basic research includes the study of the properties of a chemical. It also includes the study of what happens when 2 chemicals are mixed. So that's going back to what we said before. We're going to be studying matter and their properties, and we're going to be studying about the changes that happen. Okay? What happens when chemicals are mixed? What changes might occur? The cool thing about chemistry is we get to satisfy our curiosity about how the world works. Than anything about any science. So you get to dive into and discover what is out there for us to understand better. All right? It is an incredible, incredible world that we're able to live in, and there's so much that we can discover, and that's the neat thing about science, and in particular chemistry for us right now. Applied research, again, it's research, but it is specific research that is going to maybe have some goal involved. All right? So you're going to solve some problem with applied research. Technological development, obviously, anytime you're doing some research, there's going to be discoveries that allow you to develop something, advance something, improve something, and that may have to do with some type of technology. Okay? So new technologies are the result sometimes of certain efforts. A new technology can also result from knowledge gained from basic and applied research. So technological developments come as a result of all the research that is happening in basic and applied studies. Okay? You can answer critical thinking question number 2 there. Just pause the video, answer that, and move on. Again, it's based upon what we just talked about. All these questions are going to be based upon information in these interactive readers. Okay? All right. At the end of each section, here you can see section 1.1 review, you can answer all of these questions right here. So again, all you have to do is look back in the section, or review this video, reread what we just talked about, and you'll be able to answer all these questions. And then once you've answered all these questions throughout the entire interactive reader, you can submit it to me, and I will provide you the answers, and you can check your work and make sure that you have everything correct. Okay? All right, moving on to section 2. And again, you can pause this video at any time. Maybe you just want to finish section 1 and then come back to section 2 later on. So of course you can pause this at any time and revisit this video as you need to. All right, let's talk about matter and its properties. As we mentioned, we're going to be looking at matter and the properties that matter has. So matter, here's how it's defined. Here's what you need to know about matter. Basically, it takes up space, so it has volume. It's going to occupy certain space, a certain volume, and it has mass. So it has stuff. It's made of stuff. All right? It's not just void. It's not a vacuum. In order to have matter, you have to have material that is occupying a space. Mass is defined as the measure of the amount of material that makes up an object or substance. Now, don't get that confused with weight. Mass is just the measurement of the amount of stuff. Weight is dependent upon the gravitational pull of this Earth. If you were on the moon, your weight would be different, but your mass has not changed, assuming you went there instantaneously and didn't lose any of your mass. So mass is the amount of stuff. So the amount of stuff that's in your body isn't going to change whether you're standing at the top of a mountain or at the bottom of a valley. Your weight may be different because the gravitational pull the effect of the gravitational pull may be different from the Earth, but your mass, the amount of matter in your body, is not going to change. Okay? And then space obviously is volume. It's basically taking up space, and you can measure that volume, and we can determine that. By the way, we're going to be talking about something called density coming up, and density is the measure of mass, the stuff, divided by the volume of that stuff. So it's basically measuring how packed together is that material, is that matter. Okay? You probably already know, but atoms are the basic building blocks of matter. There are subatomic particles and even particles more minute than that, but atoms are the basic building blocks of matter. And an element is going to be any material that is a pure substance. It's made up of only one type of atom. So it's a pure substance that cannot be broken down into simpler or more stable substances. So for example, carbon, gold are elements, and those are all going to be on the periodic table. Those are our elements that appear on the periodic table. Okay? So an element is a pure substance. It has basically one type of atom. That atom is consistent throughout that pure substance. It's not a mix of different elements or a compound. This atom we consider to be the smallest unit of any element, and it maintains its chemical identity. In other words, that element has the same type of atoms throughout, and all of those atoms have the same properties. They react the same way. They have the same chemical and physical properties throughout. That's why it's called a pure substance. Now, if you take two or more elements that have their unique atoms, their unique properties, and they're able to combine, we'll talk about how that happens, then you're going to form what is called a compound. And a compound is the mixing, the bonding, the forming of a material as a result of two or more elements that are bonded together. So it can be broken down into simpler, more stable substances because it's coming from an element or elements. Okay? And each compound contains atoms of two or more elements, as I just said, and they are chemically bonded. We'll talk about the different types of bonds and how those elements are going to be bonded together. What keeps them together? Why do they bond? Why would they form a compound? Why don't they just stay as elements? What's the advantage of an element joining and bonding with another element? Why? What's the purpose? Okay? So water is an example of a compound. H2O, you probably are familiar with that. So H2O It has 2 parts hydrogen to every 1 part oxygen. Okay? It forms, by the way, a molecule, and a molecule is the smallest unit of any compound. Okay? Or it could also be an element, because oxygen, for example, is an element, but it always appears in nature as 2 oxygen atoms together. So this would be a molecule as well. Water, that's a molecule. So a molecule basically is the smallest unit of a compound, and or an element, in this case an element that has 2 or more atoms always together, and that molecule is going to retain the properties. Just like an atom retains the properties of that element, a molecule is going to retain the properties of the compound, or an element that is what's called diatomic. Diatomic means it just has 2 atoms that form up that element, okay? All right. Now, as we move forward here, you're going to realize that we study matter because it has certain properties. And those properties, once we discover those properties, we're able to use those properties and use that material because of the different properties that they have. All right? So all substances have characteristic properties. We can use those properties to identify what that substance is, what that element is, or what that compound is. All right? Chemists use properties to distinguish between different substances, as I just said, and properties can help us reveal the identity of unknown substances. We can compare those properties, and they can help us to identify a certain unknown. We can use the properties to separate different substances. Okay, so if you have a mixture of iron and aluminum shavings, they can be separated because iron is magnetic, it can be attracted to a magnet, whereas the aluminum not so much, and so you could separate the iron and aluminum that way as a result. Okay? Again, chemists, scientists like to categorize things, define things, and put things into different definitions. Here we have properties that are extensive and properties that are intensive. Here's what we mean. You should look at this prefix here, extensive, intensive. So extensive would mean like exterior or outside, and intensive, inside, within. Okay? Extensive properties depend on the amount of matter that is present. All right? So the more you have, the property is going to change. The less you have, the property is going to change. So, for example, volume is an extensive property. So as your volume changes, or the amount of matter you change, then the volume is going to change. Okay? It changes when material is added to or taken away from an object. So that would be volume, mass, or sometimes the amount of energy that it has. All of those are extensive properties. They are dependent on the amount that you have. But an intensive property does not change depending on how much of the material you have. So for example, the melting point, the boiling point, the density, all of those are always going to be the same. It doesn't matter how much water you have or how much of any material you have. The boiling point of water at a certain atmosphere at sea level is 100 degrees Celsius. Always. Doesn't matter if you've got a huge pot of it or a small glass of it. It's always the same. The density of water is always going to be the same, 1 gram per milliliter. Always the same. Doesn't matter how much you have. Okay? All right. Go ahead and answer question number 2 there. As we look at physical properties and physical changes, these are very important to also identify certain things about the material and the matter. So a physical property is something that can be observed or measured, but the substance doesn't change its chemical properties. It doesn't change its identity. It is still the same before and after the observed change. Okay? So for example, water, when it boils, it goes from a liquid to a gas, but it's still H2O. It's H2O in liquid form here, and when that water boils and turns into steam, it's still small molecules up here of H2O. It's turned into a gas. It's still H2O. It still has the same properties, still has the same chemical makeup. So a physical property is something that you can measure, but it doesn't change the identity of the substance. So one of them would be boiling point, for example. Okay? A change in a substance that does not involve a change in the identity of the substance is called a physical change. When ice melts, it's just a physical change. Okay? If you take a piece of metal and you bend it and reform it, it's just a physical change. So any change of state, what we mean by change of state means when it goes from a solid to a liquid to a gas or back, all right? Those are the different states, solid, liquid, and gas. And any time you change a state because you're going to melt it or boil it or goes through vaporization or whatever, those changes are called changes of state, and they are simply physical changes. Okay? Can answer question number 3 here. All right, I already mentioned solid, liquid, and gas here, but let's just look at some of their properties really quickly here. A solid is a solid because it has a definite volume. It's fixed. It has a fixed volume. A block of ice has a fixed volume. You can measure it, and it's not going to change as long as it's not melting. Okay, it has a definite volume and a definite shape. The particles are close together. They're really packed closely together, probably in a defined structure, what we call a lattice. So that defined arrangement or array of particles is a result of the particles being close together, packed together, not moving very much, and that would be characteristic of a solid. All right? The particles can vibrate. They still kind of move a little bit. The particles are always moving, but they're packed so tightly together and they have lower energy that they really don't move that much and they don't change their position very much. Right? They do vibrate, they do oscillate a little bit back and forth, but they're held together because of their attraction, and their low energy keeps them close together. A liquid, on the other hand, has a definite volume, but not a definite shape. So if you have liquid water and you put it in a glass, all right, it's going to fill that glass to a certain amount of volume, but it's going to take on the shape of the glass. So that's a liquid. The particles now are a little more energetic. They kind of are starting to loosen up their bonds a little bit, and they're kind of rolling and tumbling over each other. They can move, they're fluid, they can flow, they have a little more energy, and as a result, those bonds that are holding them together are not fixing them in a position. Okay? So the water spreads out. It can slide and go past each other, those different particles, and that's why they take on the shape of the container while still maintaining a fixed volume. Okay? A gas, now gas particles are getting more and more energy. They have so much energy that they actually have pulled away from each other. They've broken that bond and have pulled away from each other, and now they are free of each other and are separated. So those gas particles have lots of energy, and they have neither a definite volume because they basically just keep spreading out until they fill up the room or the container, and they don't have a definite shape. Okay, so as mentioned, as water turns into steam here, it's going to turn into that gas, and those gas particles are going to spread out. Still water, they're just going to spread out and take on the volume of whatever container they're in. They move much more rapidly, they're farther apart, they spread out, and basically the attractive forces between those gas particles are not strong enough to keep them together because the particles have so much energy. Okay? There is a fourth state. It's not very common, but the fourth state of matter, plasma, is found in fluorescent bulbs and stars, and plasma basically is often at a very high temperature, and it's a matter is made up of charged particles. So matter does spread out like, or sorry, plasma does spread out like a gas and take the shape of its container, but it is a charged particle, and it is a result basically of stripping away some of the electrons. So then the core of that atom, the nucleus of the atom, is going to be still positively charged because of the neutrons, and you have basically a charged material, okay? And so that's the fourth state of matter called plasma. All right, chemical properties and chemical changes. So we just talked about physical properties and physical changes. Also, matter can go through chemical changes, and that is then testing their chemical properties. And every element is going to have specific chemical properties. Every compound is going to have specific chemical properties. They're going to react in a very specific way because of those properties. So, a chemical property relates to the substance's ability to undergo changes that transform it into something different. You have to emphasize different. The only way, the only guarantee that you know something has gone through a chemical change is that you had something before the reaction and now you've got something different after the reaction. We can make observations. We can look at the changes and use our observation skills in order to try to determine if a physical change has occurred. We look for things like color change or gas is released. We look for heat given off or light given off, all of those. But the only definite guarantee to know if something has gone through a chemical change is to test it before and after and see if you have something different. Okay? So a chemical change is a change in which one or more substances are then converted into something different, as different properties, different chemical properties as a result. Okay? So a change in which at least one new substance is formed is called a chemical reaction. So that chemical reaction, we're going to be spending a lot of time looking at chemical reactions. Those chemical reactions often result in forming something new because something's gone through a chemical change. All right, so for example, if you have oxygen, so iron is left out, you left your bicycle outside, and the chain, it begins to rust. Well, that iron in the chain is reacting with oxygen and is creating iron oxide. You've got a brand new compound, a new substance. And the iron and the oxygen reacted to form something new. That is a chemical change, definitely. Okay? All right, go ahead and answer reading check questions 4 and 5. Okay, this diagram here is just showing you that we have iron. So this is a piece of metal iron put into this flask, and then chlorine gas, or maybe chlorine pellets down at the bottom, and it is going to turn into a gas, and the chlorine and the iron are reacting, and you can see that on that piece of metal there's forming a new substance, and that is your iron chloride. Okay, it has brand new properties. That would definitely be a chemical reaction. Okay. Anytime we have a reaction, we want to identify what is involved in this reaction. The two compounds, or maybe they're elements that are combining together, or maybe it's being decomposed, but the things that you have before the reaction, those are called your reactants. And then the object or objects, the chemicals that you have after the reaction, those are called your products. So in this case, in our diagram up here, iron and chlorine are your two reactants. They're brought together. They were separate before. You brought them together, introduced them to each other. They react and form a product called iron 3 chloride. Now, as mentioned, the chemical reaction can form products, and those products are going to have different properties than the reactants. Okay? Then you know you've gone through a chemical change. There's one important key note that we will probably come back to, but this is crucial, very, 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 very important here. Okay? Don't miss this. This is saying that anytime you have a chemical reaction, yes, you form something new, but that does not affect the total amount of matter present before and after the change. So the amount of matter, the total mass, always stays the same. Okay? So you're going to use some of the iron and some of the chlorine in order to form iron chloride, but the mass of the iron and the chlorine before the reaction is going to equal the mass of the iron, chlorine, and the new substance, iron chloride, after. So the total mass before and the total mass after is always going to be the same. You're not going to ever going to be able to create mass or destroy mass from a chemical reaction. Okay? So that's conservation of mass, and that is consistent, and it is a very, very important part of chemistry. Okay? The total mass remains the same in any reaction. Energy is a huge part of why matter goes through a reaction. Is it going to absorb energy? Is it going to release energy? So, every physical change and chemical change requires energy. Every one. Energy is key. Very important. Okay? This energy can take several forms. It can be heat energy, it can be light energy, and that energy is going to help determine what type of change takes place. So, just for example, heat can cause the change of state, meaning, remember, change of state means going from a solid, liquid, to gas, or back. Water can boil and go from a liquid and become water vapor, goes to a gas. But heat can also cause water vapor to break down into oxygen gas and hydrogen gas. So you can even add more heat, maybe in the form of an electrical current, and you can take that H2O and you can transform it into hydrogen gas and oxygen gas. So you can have an electrical current flow through water, it's called electrolysis, and you can cause that water then to even break apart and cause new products that are going to have new properties. So water going from liquid, that little L there means liquid, to water as a gas, that is simply a physical change. But it still is going to require energy to do that. To make water, liquid water let's say, turn into hydrogen gas, that's a G there for gas and a G there for oxygen gas, that is going to require energy as well. But this is a chemical change. Okay? We can track that energy, we can measure that energy, we use the descriptive properties of that energy to determine things about the chemical reaction. Okay? So we're going to keep track of that energy. Very, very important that we're going to be talking about energy a lot. Okay? Before and after the physical and chemical changes that occur. And we're talking about the total amount of energy present before and after. And we're going to be comparing those and determine if energy was released or if energy was absorbed. Okay? Absorbed or released. Always, 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 just like mass, energy is always conserved. Okay? The conservation of energy. You're not going to be able to destroy or create energy. It may change forms, but you're not going to be able to get rid of it and make it disappear or just make it magically appear. It's got to come from somewhere and it's got to go to somewhere. So that's another law of conservation, this time the law of conservation of energy. So mass and energy are both conserved when we have a reaction. Okay. All right, let's continue here and talk a little bit more about matter and the fact that matter can be either a pure substance. We mentioned that already before when we talked about elements, but also water, H2O. Water could be a pure substance because it is the same molecule throughout. All the molecules have the same properties. Or matter can be a mixture. And obviously just from the term there you can see that it's going to be a conglomeration. It's going to be a substance that has different substances, different materials, different types of chemicals mixed together. So we classify it as either pure or a mixture. A pure substance, we know it's pure because there's not going to be any variation from sample to sample. So a pure substance can either be an element or a compound. Mixtures, though, there's going to be differences throughout the mixture. It's going to contain one or more substance, and the properties are going to vary depending on the sample that you draw from that mixture. So sometimes two samples of the same mixture will be different depending on how much of the 2 or 3 or 4 substances that you have in the mixture, how much you have in your sample. Okay? So just understand that we talk about pure substances and mixtures, and we're actually going to break mixtures down even further as we continue here. So answer reading check number 7. Let's take mixtures now and let's break down mixtures just a little bit more as we talk about different categories within mixtures. So as we said already, a mixture is a blend of 2 or more kinds of matter, and each of those specific substances are going to keep their own identity and their own properties. It's just that we're going to mix them together. So that mixture is going to have a combination of those properties, whatever it's made up of, whatever substance you have in there, that mixture is going to take on those properties. Okay? We like to further break down a mixture into 2 types of mixtures. It could be homogeneous. If you look at that prefix, that's simply going to mean the same. And heterogeneous, if you look at that prefix, it's going to mean different. So homogeneous, it is uniform. It is the same throughout. It doesn't change. It doesn't matter if you grab a sample of the mixture from this place or a sample of mixture from this place. You're going to have identical samples. They're going to look and have the same exact types of substances within. Okay? Uniformity throughout. A heterogeneous mixture is one that is not uniform. You may grab a sample here and a sample here, and they're going to look different. They're going to have different properties because it's not a complete, uniform, congruent mixture. Instead, it's kind of pockets of different stuff. Okay? So, let me just give you some examples. Salt water. Salt water would be a perfect example of something that's homogeneous because it doesn't matter if you take a sample of the salt water from here or from here, it's exactly going to be the exact same composition. Okay? But you might have something like dirty water or silt in the water or maybe even a milk. Milk might be heterogeneous. Those are examples of heterogeneous because if you take a sample of milk from here, you might get a little more of the cream. If you take a sample of milk from a little different place in the container, you might get more of the water content. Okay? Silty, dirty water. You take a sample from one part of your container of silty, dirty water, you might get a lot of dirt. The other sample here might be a little clearer, so it's not going to be the same throughout. Okay? So this flowchart might help you just to kind of figure out the different ways that we categorize and compartmentalize matter. So notice the questions that are being asked. Matter, so can it be separated? No, it can't. In that case, it's a pure substance. And if it's a pure substance, can it be decomposed into It's elements. Okay? If it cannot be decomposed or broke down anymore, then it's already an element, like gold, aluminum, oxygen, chlorine. If it can be decomposed and broken down into elements, then they would be categorized as compounds, like water, sodium chloride, or sugar. Okay, back up here. If it can be separated, meaning you can just separate it using some of its properties, then we call that a mixture. That mixture then can be further broken down into, is it homogeneous, meaning it is this uniform composition throughout, or is it heterogeneous, where it is not uniform throughout, and the samples that you would gather from that heterogeneous mixture might look different. Okay? All right. We use the properties of different substances in order to separate mixtures, and you're actually going to do a couple labs using those properties. So the parts of a mixture can be usually separated, and we're using the properties because the properties of different substances are different, and as a result we use those differing properties to separate them in different ways. So separation is possible. For example, passing some mixtures through a filter will separate certain components. Why? Because some substances are so tiny in their nature and their makeup that they can pass right through that filter. Other substances cannot. So the size of the particle is actually going to be the property that allows us to filter out some, and others will pass through. Okay? Particle size. We're using that property. Here are some other methods of separating. Centrifuge. A centrifuge spins the solution, spins the mixture, and the heaviest ones are going to go at the bottom. All the solids are going to go at the bottom, and that's one way to separate based upon their property. Okay? Chromatography. Chromatography, you're going to do a lab, I believe, dealing with chromatography. It has to do with the polarity of the molecules and how polar they are, meaning how much attraction they're going to have to water molecules or some other molecule, and you'll be able to separate them across a piece of like filter paper or something like that. Okay, you'll see it when you do the lab. Okay, it talks about the different methods of separation here. It talks about a centrifuge, and it talks about chromatography, so you can read about those right there. All right. It says here those mixtures can be either homogeneous or heterogeneous. Any sample of a pure substance is homogeneous. So if it's a pure substance, pure water, for example, pure could be, yeah, let's say water. Water is a good example. That pure substance has a fixed composition, like H2O. Okay? So every sample of a pure substance has the same physical and chemical properties. We kind of already have addressed that. Okay? And you can read on here. Every sample of a pure substance has exactly the same composition. So, as I already mentioned, water has 2 parts hydrogen, 1 part oxygen. Well, hydrogen is lighter than oxygen, and so by mass, it is always going to be 11.2% hydrogen and 88.8% oxygen. Even though it has twice as many particles of hydrogen as oxygen, the hydrogen is so much lighter. So by mass, if you were to actually calculate the mass and find the mass, every water molecule or any sample of water, doesn't matter how big or how small, by mass, it's always going to have 11.2% of its mass would be hydrogen and 88.8% of the mass would be oxygen. Okay? Okay, reading check number 9 and 10. You can answer those now. Anytime we look at compounds, we know that compounds are made up of 2 or more elements, and those can be broken down. They can be decomposed. Breaking down is decomposition. Okay? Pure substances are either compounds and elements. A compound can be broken down into 2 or more simpler compounds or elements, and that would definitely be a chemical change. Okay? Mixtures can usually be separated just by looking at their physical properties, like magnetism or size of the particle, things like that. Does it dissolve in water? Okay? We don't really need to talk about laboratory chemicals and purity. It's just saying basically that chemicals in labs are treated as pure, even though there may be contaminants in them. Okay? And it's just talking about different grades of chemical purity here. You don't need to worry about that. All right? You can answer number 11 here. You can just use this diagram in order to answer number 11. You'll notice there's a picture here and a picture here, and talking about the grade of the chemical. I'll let you look at that, okay? As I mentioned at the end of every section, there are questions, so you can go ahead and answer these questions. You can pause here, answer these questions, and then I'll look at it and return you the answers when you submit it. Okay, let's spend a little more time talking about a very important part of chemistry. And remember, we talked about elements, those pure substances that are all found on the periodic table. They all have the same atom throughout, and that atom is always going to have and carry the same properties. All right? They're pure substances. They cannot be broken down any further into more simple or simpler chemicals. And each element has its own properties, chemical and physical. Okay? On the periodic table, chemists have organized these elements in a specific way. And this was developed and discovered over the course of many years, and they began to see patterns as they began to organize and arrange the elements in different ways. So we use the name, there's a name, there's a symbol, and then there's lots of other data attached to each element, as you'll see in the periodic table. All right? The complete periodic table that includes the names of all the elements can be found in the chapter called Periodic Law. So we'll be talking more about the periodic table later on, but this is just introducing you to it right now, okay? So all you need to know right now is that the periodic table organizes the elements according to their properties. All right? On the periodic table, every element's got a little square, and in that square, you're going to see lots of information. It shows the symbol for that element, the atomic number. We'll talk about what that is. It'll give you the name, maybe the mass, and sometimes some other information. Okay? Sometimes the name may make sense along with its symbol. Other times the name and the symbol don't make sense that they would go together, and that's because sometimes the symbols come from some other modern language, such as Latin or German. So for example, for iron, you wouldn't think iron, you would use the symbol Fe, but that's because it comes from the Latin word ferrum. Okay, just so you know. On the periodic table, we talk about columns and rows. The vertical columns are called groups, and those are in those groups because they have very similar properties. So anything that is in the same column or group, they have similar properties. The elements in a group are referred to also family. So everybody in the family kind of looks the same, maybe behaves similarly, and as a result, it's the same with elements. All of the elements in a vertical column or a group or a family, they're all going to have similar properties. They're going to behave in a similar manner. We have 18 groups, so they're numbered 1 to 18 from left to right, and each group contains elements with similar chemical properties, as I already mentioned. Okay? Here is an example of a periodic table. So this is group 1, 2, 3, 4, etc., all the way over here to 18. And we're going to learn why is this periodic table arranged the way it is. And it all has to do with properties. Okay? And those properties are all the result of how the electrons behave. So these are intertwined. Those are connected. The properties, this is arranged in a specific way because of the properties of the elements, and those properties are a result of how the electrons are arranged and behave in each of the atoms of those elements. Okay. You'll notice that the metals are mostly over here on the left side of the periodic table. The nonmetals, there's fewer of them. They're over here on the right side. And then metalloids are they're kind of in between. They have properties of both metals and metalloids, and they're right here along the border between metals and nonmetals. Okay? And we'll talk about this group down here, but for right now, we'll just leave it be. The horizontal rows, each row that goes across here, that is called a period. And you go across the row, and you'll see why we start a new row, but you go across a row, that's one period, and you'll see why we start another row here, and another row here, and it'll make more sense as we move forward, okay? There is definitely a regular pattern here. There is a systematic way that these are organized, and that pattern is reflective of the properties and the electron arrangement, okay, called the electron configuration. So elements that are close to each other in the same period tend to be more similar than elements that are far apart. So if things are in the same group, or maybe they're in the groups next to each other, they're all going to have similar properties, or at least more similar than if they're far, far apart. Okay? The two sets of elements placed below the periodic table make up what are called the lanthanide series. That's down here. This is the lanthanide series because it goes from this element here, number 57, and then jumps down here. That element, number 57, is called lanthanide. So then it spills into this row, which is called the lanthanide series. We'll talk about that. And the other one is the actinide. Actinide here, number 89, is, I think it's actinium maybe. Actinide then spills down here into this row. So this row down here below is called the actinide series. And the only reason that they're pulled out, the only reason these rows are pulled out and put below sometimes, is just because if they were placed in there, the periodic table would be very, very wide. So they're just pulled out, placed below, and then the periodic table is pushed together just to make it a little more compact. That's the only reason. Okay? You can answer reading check number 2 here. As I mentioned already, we got metals on the left, nonmetals on the right. And then we've got the metalloids, like boron and silicon metalloids are in the middle. All right? Some properties of a metal. So you know they're mostly on the left, right? They're all on the left or center of the periodic table, but metals have certain properties. And you should know these. They conduct electricity, they conduct heat, they are mostly solids at room temperature. Mercury, for example, would be an example, or would be an exception. Mercury is a liquid, actually, at room temperature. Most of the metals are malleable, meaning that you can bend them, shape them, you can flatten them, you can pound them into sheets, okay? And they're also ductile. So ductile means that you can stretch them, you can pull them, you can make them into wires, like copper wires. All right? And often they have a little bit of a shine to them. They have some luster. There are exceptions, of course. I said mercury is a liquid at room temperature. The metals in group 1 are often soft, and they can be cut with a knife. And but they are also still very much electrical conductors, and they conduct heat. They're also very reactive. Metals are sometimes very reactive. Okay? Here's just, you can read this. I'm not going to read this for you or go through this for you. It's just talking about copper as a typical metal, and it's talking about some of the properties of copper which you might be familiar with already. Okay? Answer question 4. A nonmetal, you can see right away there's differences. It is not a good conductor of heat nor electricity, so it doesn't conduct either of those. And you'll notice that there are many more metals than there are nonmetals. So the nonmetals are usually Sometimes they're gases at room temperature, like nitrogen, oxygen, fluorine, chlorine. Okay, not always. Bromine is a liquid at room temperature. And solid nonmetals include carbon, phosphorus, selenium, sulfur, iodine. Some of them are solids, and there's some examples of these. Okay. Nonmetals tend to be, at least in their solid form, they tend to be brittle, meaning they break apart easily when you put pressure on them. You maybe try to apply, maybe if you hit them with a hammer or something like that, they're brittle, they break apart. And they are not malleable, nor are they ductile. So they are brittle, and we'll talk about why that is. Okay? Here's, again, you can read this about phosphorus. Here's an important group of nonmetals. Those are the noble gases, and they are found right here at the end of the periodic table. So this group 18 are all noble gases, sometimes called inert gases, because they do not react very well. They don't react hardly at all. Not that they don't ever, but they resist being active and reacting. We'll talk about why that is. So those noble gases are in group 18, and they are, as I mentioned, gases, and they are unreactive. They don't like to form compounds. They like to be by themselves. They're very independent. Okay? Metalloids, I already mentioned, they have characteristics of metals and nonmetals together. So it actually, they can be very useful in their own right. Okay? For example, semiconductors. Those are metalloids. Silicon, for example. Okay? Number 5, you can answer that one, and then you can go on and read and answer all the questions here in section 1.3. All right? You can spend some time looking at this here if you need to. If you need a little review on converting units, going from one SI unit to another, and learning these different prefixes here, that might be helpful if you need to review that. Okay? All right, and then the last thing that you need to do in order to complete this interactive reader is at the end of every chapter, there is a chapter review. So you're going to answer all of these questions here and go through all of these. And then once you submit this and I look at your answers, like I said, I will return the answer sheet to you so you can check your work and then tell me if you have any questions on those that you may have missed. Okay? All right, that concludes Chapter 1 for chemistry, and we'll keep plugging along. Let me know if you have any questions. The future videos may be a little more concise, but this is the first one, so I'm going to give you just a good introduction and a thorough explanation of the material in Chapter 1. Okay? All right, keep up the good work.